This lesson is about phase equilibrium. Let's talk about the famous PV diagram, the phase diagrams, and then talk about phase equilibrium situations. Alright, so let's start with the PV diagrams, the pressure and volume diagrams. They're very useful, okay? So we can remember the ideal gas formula. That's PV equals nKT, pressure, volume, number of molecules, Boltzmann constant, and absolute temperature. Also, if we make this pressure and volume constant, okay, so if we trace lines making P and V constant, we would have something that looks like this. Okay, we have a diagram that's relating pressure and volume. So we have constant pressure lines and constant volume lines in the vertical. If you trace for a substance these lines, where pressure and volume are constant, we have this format here, okay, this dashed black line. Now, these blue lines here are actually the isotherms. So these are lines where we have constant temperature. So note here, for any substance, we would have something that looks like this, okay? On the left side of the black line, we have the liquid state. On the right side here, we have vapor, right? We have gas. In between, we have what you call the liquid vapor region. So in this part here, we have some amount of liquid and some amount of vapor, right? Note that in this region, the temperature for the isotherms here, the pressure is constant, okay? So every time something is changing phase, their pressure is constant, and we see that also that the temperature is also constant, okay? So for different levels of pressure, we have different isotherms, different constant lines of temperature, right? This point here is also important. This is called the critical point. Okay, in this point here, we don't have liquid. So everything here, we don't have like a change of phase. So everything goes directly to vapor here. Above this critical pressure and the critical temperature, that's called the critical point. Let's take a look now into this phase diagram, okay? This example is the phase diagram of water. So we are relating pressure now with temperature, right? It's not volume anymore here, it's temperature. So for the water, we have three lines here dividing the phases, all right? On the left side, we have the solid state. In the case of the water is ice. We have this part here, water, liquid water, and here we have steam, the vapor phase. Okay. Something very important here is this point here that we call the triple point. In this point, all the three phases coexist in one point. So for water, we have a pressure of 0.06 atmosphere and 0.01 degrees Celsius. At this point here in water, we have the three phases coexisting. Okay. Now, if you change phases, we can change from the liquid to the steam, and this is called the vaporization. If we go back into this line here, we have condensation from vapor to liquid. Also, on this other line here, if we go from water to ice, we have freezing, and from ice to water, we have melting, the melting process. Okay? And also, we can go directly from the solid state to the steam state or to the vapor state. This is called sublimation. If we go back abruptly from steam to ice, we have something that we call deposition. Okay? Above the critical point here, remember from the last diagram, the critical point, here it's the critical point represented in the phase diagram. After this, we have something that we call supercritical fluid. So everything here is a very sparse gas. Okay, the molecules are very sparse. That we have very high temperatures and very high pressures. This is the supercritical fluid. Okay, let's talk about the phase equilibrium. All right. So we call that if a substance is in a closed container at a boiling point, then the liquid is boiling and the gas is condensing at the same rate without net change in the relative amount. So in this case here we have equilibrium. Also, if the temperature and pressure are increased for equilibrium state, the equilibrium is maintained by the same increase of boiling and condensation rates. So what does it mean? So take a look into this diagram here. Again, now we have temperature and specific volume. Okay, and these are lines of constant pressure. This is a TV diagram. Okay. So it means that, for example, we are in this region here, right, where we have the boiling point, so it's 100 degrees Celsius and some different in 1 atmosphere. Okay, so here is the water starts to boil. Here we have this mixture of water and vapor until it totally evaporates. So here we have an equilibrium. We have 100 degrees Celsius at approximately 1 bar of pressure and everything is in equilibrium. If we change, for example, the pressure, if we increase the pressure and the temperature, we can get to this other line here. This other line, we also have equilibrium, but now at a different temperature and at a different pressure. All right. So for a two-phase liquid vapor mixture, the ratio the mass of vapor present to the total mass of the mixture is called the quality. So it's basically the ratio between the mass of vapor divided by the mass of liquid plus the mass of vapor. Okay? Okay, take in consideration all the things we talked about and think about the situation here. So we have a pressure cooker that contains water and steam in equilibrium at a pressure greater than atmospheric pressure. All right? So how does this greater pressure increase cooking speed? So why, if we use a pressure cooker, why does it increase the cooking speed of the food you put into? Think about it, write your answers in the comment sections, and see you later.
Thank you for watching this video, and we hope you have a great day ahead. Bye bye!